Hi everyone, and I hope everyone is doing very well. Welcome back to my channel A in Economics. So in today's video, we are going to discuss another problem set. This will be problem set number 2 in Econometrics, where I will discuss one numerical question on the multiple linear regression model. So if you have seen my Econometrics playlist, I have made a detailed playlist on Econometrics where I have given you 25 long form lecture videos. Along with that, in the previous video, I have solved problem set 1 where I have solved questions regarding classical linear regression model or two variable linear regression model, right? That is already been done. Now, in today's video, which is going to be the final video in this playlist, we will discuss about numerical questions regarding multiple linear regression model, and I will show you step by step how to solve them, right? So let's take a look at this question. So if you look at this question 1, this question has all the, this question contains all the approaches that you need to know for your undergraduate or postgraduate level multiple linear regression model analysis, right? So I have given this question in such a way so that you know how to solve each of the parts of the question and you have, clarity regarding the multiple linear regression model. So let's see carefully what this question is asking. So this question has given you a model like this. The model is this: yi equals to beta naught plus beta 1 x1i plus beta 2 x2i plus ui for all I. Right? So it is definitely a three variable linear regression model where yi is the dependent variable and you have two explanatory variables, namely x1 and x2. This is given to you for all I. Now, there are some more details or some additional information that are provided. Firstly, n equals to 100. Number of observations that you are taking into account is 100. Summation small yi square. Now, see all these things that are given to you, they are in small. Small letter means in the deviation form. So, this small yi, if you write I from 1 to n small yi square, it basically means we are implying this yi minus y bar whole square, right? So this we have discussed multiple times while discussing the lecture videos. That small yi, small letter means the deviation form. In econometrics, wherever you are writing the small letters, it means you are taking this kind of a deviation form. So all the things that are given to us here are in the small letters mean we are talking about the deviation form, right? So this is the first observation. Now see, these data are given to you. Summation yi square is this. Summation x1i square, summation x2i square, summation x1i yi, summation x2i yi, and summation x1i x2i. All these values are given to you. Now, what you have to do, you have to find out the following 5 parts of this question. The first part is asking you to compute the OLS estimates of beta 1 and beta 2. See, beta 1 and beta 2, these are the two slope coefficients in this model. Beta naught is the intercept coefficient, only intercept coefficient, and beta 1 and beta 2, they are the slope coefficients corresponding to the explanatory variables x1 and x2 in your three variable multiple linear regression model. So you have to, this is the first part of this question. Now, from the lecture video, if you remember, if you have followed my lecture videos, I have derived what will be the estimated value of beta 1 cap under OLS and what will be the estimated value of beta 2 cap under OLS. So if can you recall this thing? I hope you can recall this thing. If you haven't watched those videos, I'll give the link in the descriptions. Please check that out. Here I will not derive the thing. I have already derived it in the lecture video. And in order to solve this question, here I will only write the formula directly, right? So the formula was something like this. Beta 1 cap OLS will be summation I from 1 to n. Firstly, you have x2i square into summation I from 1 to n x1i into yi minus you have I from 1 to n x1i x2i summation I from 1 to n x2i yi upon whole divided by summation I from 1 to n x1i square summation I from 1 to n x2i square minus summation I from 1 to n x1i, x2i, and a whole square of that, right? So this was the entire formula of beta 1 cap. Beta 1 cap is what? It is the slope estimate of the slope regarding the variable explanatory variable x1, right? With regard to variable x1. And I have derived this entire formula beforehand. Again, I'm saying if you haven't watched those videos, please check that out. You will get to know how to derive this thing, right? We have derived this. We have formed the normal equations, we have solved the equations, and we have got this kind of a formula. And everything that every variable that I have written here is in the deviation form. And you know all the values here are given to you in the question. So let us see what is the value of summation I from 1 to n. So here, anywhere you have n, you can consider it to be 100, because see, in the question they have given you that n is equals to 100. So we will consider each of these variables n is equals to 100. I'm not writing it again. So please take note of that, that I is varying from 1 to 100 in all of these cases, right? N equals to 100. Now, if I from 1 to n x to I square, what is x to I square? X to I square is simply 3. What is summation x1i yi? X1i yi is simply 30. Then you have minus x1i x2i. This will be simply 0. And then you have x2i yi, which will be simply 20. So this is the numerator, and what will be the denominator? x1i square into this minus this thing is again 0. So 0 whole square is again 0. So what will be the value? In the numerator, you have 90. In the denominator, you also have 90. So the value will come out to be 1. Right? So this is how you find out the beta 1 cap OLS, in our particular model, right? This is the slope parameter corresponding to the explanatory variable x1. Now, in the similar fashion, we have to find out what will be the slope parameter beta 2 cap OLS, Again, you can pause the video and think for yourself what was the formula. Formula was this. N is 100 here, x1i square. Now, it will start from x1i. In that video, I have also given you the tips how to remember this formula. I know this looks a little messy. It's a little hard to remember this big formula, but there I have, given you the tips how to remember this thing easily. It is just the interchange of 1 and 2. Only the suffix will change, and the denominator is absolutely the same in both the cases. So please watch that video, and that will help you to get this. Okay, summation I from 1 to n, x1i square. The denominator is absolutely the same. x2i square minus summation I from 1 to n, x1i, x2i, and a whole square of that, right? So again, do the same thing, put the values. x1i square, x2i yi is 20. Then this is 0 into 30 upon the denominator remains the same. 30 into 3 and minus this is 0. So in the numerator, you will have 600. In the denominator, you will have 90. So if you calculate, it will come out to be 6.67. Hence, beta 2 cap OLS will come out to be 6.67. Right? So this will be the answer for part A of this question. Answer for part 1 of this question, which has asked you to compute the OLS estimates of beta 1 and beta 2, which we have done, right? So I hope this much is clear. Now let's move to the second part. It is saying compute R square. R square is the goodness of fit measure. R square and adjusted R square. I have also taken separate classes on what is R square, what is adjusted R square. Why do we need adjusted R square? How to find that out? Again, if you haven't watched that, please check that out. So what was R square? If you remember the formula of R square, this is part 2. R square was simply ESS upon TS, right? You have to individually find out what was the value of ESS, what is the value of TSS, and just divide it to find out the value of R. Now, if you remember ESS, what will be ESS in this particular scenario? See, this is the model. This is your model. Now, can you tell me what will be What will be ESS here? Look at this model and tell me what will be the ESS here. If you remember, ESS will be simply beta 1 cap, that is beta 1 cap OLS into summation I from 1 to n yi x1i, this will be the first term, plus beta 2 cap OLS and then summation I from 1 to n yi into x2i. Again, I am not deriving this because I have done that before. I will only use the formulas here, right? If you want to know the derivation, please check that out. I will give the link in the description, also in the I tab button. You will get there, right? So beta 1 cap. So what is the value of beta 1 cap? We just found out in the previous part. It is simply 1. This is 1. Now yi x1i, this is given to you in the question. This is 30. Plus, what is beta 2 cap? 6.67. This is 6.67, and what is summation yi x2i? This value is 20. So here you will have 30 and here you have 133.4. So if you calculate, it will come out to be 163.4. Right? 163.4. So ESS is done. Now what is TSS? TSS is simply what? This. Small yi square. This will be TSS, which is nothing but the expression which I wrote before. Yi minus y bar whole square. Now this expression is directly given to you in the question. What was that? 493 upon 3. So this is 493 upon 3. If you calculate, this value will come out to be 164.33. 164.33. This will be the value of TSS, right? Now, if you know what is ESS, if you know what is TSS, you can simply find out this ratio. So ESS is 163.4 and TSS is 164.33. If you divide, R square will come out to be 0.99434, right? Or approximately R square will be 0.99, right? So it is a very, very good model according to our data set. According to the sample data that is provided to us, that is a sample of 100 observations that are provided to us, it is suggesting that approximately 99% of the entire variation of the dependent variable y can be explained with the help of independent variables, namely x1 and x2, right? So in our model, we have seen that we have two explanatory variables. R square 99 means what? 99% means what? 99% on an average, 99% of the entire variation of this dependent variable y can be found out using the explanatory variables, that is x1 and x2 in our particular model, right? So this is how you compute the value of R square. Now, how to compute the value of adjusted R square, which is R bar square. So let us do that. If you remember, adjusted R square is something like this, R bar square, where what we do, we adjust the R square with the corresponding degrees of freedom, right? While teaching you the adjusted R square, I have said what you have to do, you have to divide the RSS and the TSS with their respective degrees of freedom, and that would give you your adjusted R square. And why we do this? Because we know as you keep on adding explanatory variables in your multiple linear regression model, your R square will always go up, because R square is a linear function, is a linear monotonic function of your number of explanatory variables in your model. But this may not be always capturing the real life scenario, because some of the variables in your model may be statistically insignificant. But still, R square will show you that if you add those statistically insignificant variables also, your R square will go up. R square cannot fall, right? R square can never be going into the negative direction. It will remain the same or it will increase as you keep on adding your explanatory variables in your model, which is not the ideal scenario. That is why you have to adjust your R square with the corresponding degrees of freedom, and that is why we have found out what was adjusted R square. What was the formula for adjusted R square? It was simply 1 minus RSS upon the degrees of freedom of RSS. What is the degrees of freedom of RSS? It is simply n minus k. K is the number of parameters that are present in your model, including the intercept now. And in the denominator, you have TSS upon the degrees of freedom. What is the degree of freedom of TSS? Which is simply n minus, right? So this was the formula. So basically, you can rearrange it a little bit. So you will get RSS into n minus 1 and TSS into n minus. So this is basically you are taking it on the numerator and taking this thing in the denominator, right? Now, what will be the values? Let us see. So we already know what is the value of TSS. We already know what is the value of TSS and we already know what is the value of ESS. Now, using these two information, can we find out what is the value of RSS? Definitely yes, because from the decomposition property of TSS, we know TSS is simply ESS plus RSS. So how do you find out RSS? RSS is simply TSS minus ESS. Right? That will give you your RSS. Now, if you do that, I have already done that for you. So the value of R squared will come out to be 0.93. So you can do this in your free time. So see, the expressions are given to you. This is TSS, this is TSS. So simply take the subtraction. Do the subtraction, you will get this kind of a thing. 0.93 approximately. This will be 0.93. This will be the RSS. Now, if you have this RSS, see all the rest of the things you know. You already know. So you can simply put the values. 1 minus 0.933. Then n minus 1. N is 100. So n minus 1 is 99. Upon TSS. TSS was 164.33. And what is n minus k? N is basically 100 and k is basically 3. See, number of parameters in your model including the intercept. So 1, 2, 3. You have these 3 parameters in your model including the intercept. That is why the value of k is 3 here. The value of k is 3 here. So it will be 97, right? 100 minus 3, that is 97. Now you can do this calculation on your own. I have done that already. The value that you will get is approximately like this, 0.9943. Previously, what you have got? 0.9943. And here what you see? 0.9942. So R squared and adjusted R squared is almost giving you the same answer, right? This is 0.9942 and this is 0.99434. So approximately R squared and adjusted R squared is giving you same result. And so we can say, we can conclude that this is a very good model, right? In terms of fitting, in terms of statistical fitting, this model is very good because most of the variation of the dependent variable y can be explained with the help of independent variables, and that is proved by both R square and the adjusted R square. Even if you adjust your R square with the corresponding degrees of freedom, then also you'll see that the 99%, approximately 99% of the variation is still explained of the variation of the dependent variable. That is why it is a very good model, very good fitted model. So x1 and x2 are statistically may be statistically significant and they have the most of the explanatory power. That is why the fitting of the model is very good, right? So this is the second part of the question. So we have computed both the R square and the adjusted R square. Now let's move to the third part of the question, which is asking you, let me remove these things. So what is the third question? Third question is saying test the hypothesis that H naught beta equals to 0 against H1 beta 2, beta 2 equals to 7 against H1 beta 2 not equals to 7. So basically you are trying to do one sample t-test, basically two-tail test, and you have to find out if the slope parameter corresponding to x2 can take the value 7 or not, and we'll assume that we are taking into account 5% level of significance, right? If you take that into account, so what will be the approach? How will you solve this question? So this is given to us that H naught is beta 2 equals to 7. This is your null hypothesis, and you want to check versus the alternative beta 2 not equals to 7. So in this kind of questions, which is the individual test, remember we have said there are two kinds of tests. One is the individual significance test and one is the joint significance test. Here it is an individual significance test. We are trying to find out if x2 variable is significant or not, and it will take a specific value or not at 5% level of significance. So alpha is basically 0.05 and it is a two-tailed test. Since the alternative is like this, you will have two rejection regions. It is a two-tailed test. It is a two-tailed test, right? So the first thing that we want to know in our problem is that what will be the appropriate test statistic. For that, we know this fact that what will be the distribution of beta 2 cap. If you remember, beta 2 cap follows a normal distribution which satisfies the blue property. That is why the mean is this and the variance will be simply this, right? In case of hypothesis testing, we'll always assume the estimates follow a normal distribution for our simplicity. It's not an assumption, it's just for simplicity, we assume this. It's easy to work with. And for large sample, all the sampling distribution will move towards the normal distribution by the central limit theorem. That is why also you can use this normal. Assume that this is following a normal distribution. So beta 2 cap follows normal distribution with mean is beta 2 because it is an unbiased estimator of the population parameter beta 2 and the variance is beta 2 cap. If you have this, you can define the t statistic, or let me write the test statistic. Test statistic will look something like this. T. Test statistic is T, where you have beta 2 cap, the estimated value of beta 2 cap minus the value of beta 2 under H naught. That is this value of beta 2 under H naught upon the standard error of beta 2 cap, right? Estimated standard error of beta 2 cap. So this is simply the square root of the variance. Under H naught, this will follow T distribution with n minus 3 degrees of freedom. N minus 3. So here see you have three parameters. Degrees of freedom is total observation minus the total number of restrictions you have in your model. Here you have three parameters, that is the three restrictions are there. That is why it will be n minus 3. Now all you need to do, you need to find out what will be this test statistic. You have to compute what will be this test statistic, and that will give you the hint of solving this question, right? So in order to find out the test statistics C, beta 2 cap is already known to us. In the first part of the question, we have estimated the OLS estimator of beta 2 cap, that is done. We also know what is beta 2 value, population parameter value under H naught. So the only thing that you have to find out is the standard error of beta 2 cap. And for that, you have to calculate the variance of beta, right? So let us start by computing what will be the variance of beta 2 cap. So variance of beta 2 cap in the MLRM setup will look something like this. Sigma u cap square, this is the error variance, right? Error variance into summation I from 1 to n x1i square upon summation I from 1 to n x1i square summation I from 1 to n x2i square minus summation I from 1 to n x1i, x2i and a whole square. When I'll go into the matrix notation, I'll again explain how to get this formulas. I have already derived this before. I'll again explain this when I will go into the matrix notation. So now you have all the formulas. No, you don't have the formula for this. So let us try and derive this formula. So if you remember what was the error variance formula? Error variance is simply RSS upon n minus 3. So for two variable, it is n minus 2. For three variable, it is n minus 3. For in general k variables, it is n minus k, right? So RSS value is already known to us, 0.933. Previously, we have seen this. N minus 3 is simply 97. If you do that, you will get 0.0096185, something like this. So approximately 0.009 you can consider. So if you now substitute the values here, what you will get? 30 into 0.0096185. In the denominator, you have exactly the same thing that we have got before. We got it to be 90. This thing is 0, this is 30, and this is 0. So this is 90. And approximately this value will come out to be 0.003206. You can do this on your own. I have already calculated this. The variance of beta 2 cap will come out to be this. So what is the standard error of beta 2 cap? Simply the square root of the variance of beta 2 cap. So that will come out to be 0.05662, something like this. Now you have all the values to compute the t statistic. So let us do that. T computed. So beta 2 cap estimate. First, there will be the estimated value, which is this, minus under H naught, the value was 7. And now in the denominator, you have this standard error. If you compute this, this will come out to be minus 5.8280. So what is the absolute value of T computed? Absolute value will be 5.8280. And what is the T critical value? The critical value will be, since it is a two-tailed test, we will divide the significance into two equal halves, 0.025, and degrees of freedom will be 97, right? N minus 3 basically. This is, and if you see from the statistics books, this will approximately be equals to 2. The value, you can check it for yourself. It will be close to 2. So the thing is like this. If you draw this T distribution is always symmetric about 0. So here you will have two rejection regions. This is one rejection region. This is the other rejection region. The value here will be 5.8 and the value here will be the critical value, which is 2. And here it will be minus 2. This is the critical value. And what is the computed value? Computed value is way here, 5.8 something, which definitely falls into the rejection region. Right, which definitely falls into the rejection region. So what we can say is that T computed is strictly greater than the T critical value. Hence, we should reject H naught. We should reject H naught at 5% level of significance, right? So this will be the answer for this question. So basically, we should reject H naught means the alternative is accepted, which is beta 2 can't be equals to 7, right? We are rejecting this null hypothesis means that we are accepting the alternative at 5% level of significance, beta 2 can't be equal to 7. That will be the conclusion for this part of the question. Let us go back. So 1, 2, 3, all these parts are done. Now let's look at the last two parts. Part 4 is saying test the hypothesis. Now see, this is the joint significance test. Now it becomes joint significance. So I have, given this question in such a way that you know how to solve each of the, things that you need to know in MLRM, right? You need to know what will be the estimated values, what will be R square, what is adjusted R square. You know how to solve hypothesis testing problems, right? So you can tackle each of the parts. You can, answer questions from MLRM from different directions, right? So that is why it is an all-in-one question. I have tried to give you that. So part 4 is asking you test the hypothesis H naught is beta 1 equals to beta 2 is 0 against the alternative beta 1 is not equals to 0 or beta 2 is not equals to 0. Now it is a joint significant test. For that, we always use the if statistic, right? We always use the if statistic for joint distribution. So let us do that. We want to test H naught is beta 1 equals to beta 2 equals to 0 versus the alternative looks like this. Beta 1 not equals to 0 or beta 2 not equals to 0. Right? This is what is given to us. Beta 2 not equals to 0. So required test statistic. Required test statistic. That will be if statistic, where the statistic will look something like this. ESS upon the degrees of freedom of ESS upon you have RSS upon the degrees of freedom of RSS. Now ESS, what is the degrees of freedom for ESS? Can you tell me what is the degrees of freedom? It will be simply K minus 1. K is the total number of parameters, that is 3. So it will be simply 2. And what is the degrees of freedom here? It will be simply N minus K, which is 97 basically in this case. So let us compute the value. If computed will come out to be ESS we earlier found out to be 163.4 upon this K minus 1 will be 2 RSS is simply 0.933. This also we got earlier and it is 97. So this computed value will be 8493.997, something like this, right? This is the F computed value, and what is the F critical value? Critical value will be 0.025, sorry, 0.05, and then the degrees of freedom. So this is 2 and this is 97. At 5% level of significance, this is 0.05, and then you have the first degree of freedom and the second degree of freedom, 2 and 97. If you see from your statistic books, this will come out to be 3.15. 3.15. So it is way less than the computed value. So again, the computed value is strictly greater than the critical value, right? Computed value is strictly greater than the critical value. If you draw this in a diagram, so F distribution looks something like this. Longer tail towards the higher value of X. This is the F distribution. So you will have two rejection regions, and this value will be 3.15, and the computed value is way higher, somewhere here, 8493 something something. So it's definitely in the rejection region on the right hand side. Therefore, we will say we will again reject H naught. We will reject H naught at 5% level of significance, and we will conclude that either beta 1 is not equals to 0 or beta 2 is not equals to 0. That is, one of them, at least one of them will be statistically significant, right? So here the null hypothesis is saying that no variable is significant. X1 and X2, both the variables are insignificant, but that cannot be so, because see, we have got that R square to be very high, right? R square to be very high. R square is 99%. So definitely one of them must have been significant. Ideally, both the variables are very much statistically significant. That is why the R square and adjusted R square is very high. So the alter will basically accept the alternative hypothesis that beta 1 not equals to 0 or beta 2 not equals to 0, which means at least one of the variables, explanatory variables x1 or x2, has to be statistically significant. But ideally, intuitively, we can understand that both will be statistically significant here, right? So beta 1 is not equals to 0 or beta 2 is not equals to 0, right? So this is the fourth part of this question, and the final part of this question is asking you, test the hypothesis H naught. Now you have a relationship between beta 1 and beta 2. This is a unique kind of a question. See how to handle this question. So beta 2, H naught is beta 2 equals to 7 beta 1, against H1 is beta 2 not equals to 7 beta 1. So let's see. Let's see how we can solve this part of this question. This is a little unique. I hope you have not done this thing before. H naught is beta 2. So they have given you beta 2 equals to 7 beta 1. So instead of writing in this way, what you can do, write beta 2 minus 7 beta 1 equals to 0. So in H naught, in the null hypothesis, we always try to equate it to 0, right? We always try to, unless and until a specific value is given. For example, here in this question, they have given you a specific value of 7. Unless and until this kind of specific value is given, we always try to write the null hypothesis so that in the right hand side we have a 0, right? Right hand side we have a 0. So always take everything to the left hand side. Everything take it to the left hand side, versus the alternative is beta 2 minus 7 beta 1 is not equals to. So this is the first step. This is how you have to write this. Now we will use the same approach, only the calculation will be a little different. So here, what will be the test statistic? If you can calculate the test statistic in a proper way, then your problem is 90% solved. So test statistic will look something like this. Understand this thing, it will again be T statistic. But here, instead of one parameter, you have two parameters, both the parameters, beta 1 and beta 2. So how do you write that? Firstly, write the computed value. So beta 2 cap minus 7 beta 1 cap. So when I say estimated value, this is the OLS estimated value, minus the value of the parameter, the value under H naught. Under H naught, what is the value? The value is this. So this entire value under H naught upon, what will be the thing? It is the standard error of beta 2 cap minus 7 beta 1 cap, right? So this will be the test statistics. So see, when we have for a single parameter, suppose beta 2 equals to 0. So suppose we want to test this particular thing. Right? If this was the scenario, what we have done is that t will be beta 2 cap minus beta 2 under h naught and then standard error of beta 2 cap. So this will be the formula. So now you can match it. Formula structure remains the same. Firstly, you will write all the computed values, all the estimated values. Beta 2 cap, you have beta 2 and beta 1 here. So you'll write beta 2 cap minus 7 beta 1 cap minus everything that you are given in the under h naught. So this entire value under h naught, that will be 0 here. Under that, in the denominator, you have standard error of this entire, right? So all you need to do is to compute the standard error, because see, beta 2 cap and beta 1 cap is already, found out in the first part of the question itself. This value is 0. So all you need to do again to find out the standard error, right? So how do you find that out? Okay, let me first write what will be this value. Beta 2 cap OLS minus 7 into beta 1 cap OLS. Beta 2 cap was 6.67 and 7 into beta 1 cap OLS is only 1. So this will come out to be minus 0.3. So this will be the numerator. This is the numerator. Now, in the denominator, you have to find out the standard error of beta 2 cap minus 7 beta 1 cap. So let's start with the variance and then we will take the square. So you have to find out what is variance of beta 2 cap minus 7 beta 1 cap. Right? So what will be this formula? Now, remember that variance of ax plus by. What was this formula? What is variance of ax plus by? It is simply a squared variance of x plus b squared variance of y plus 2ab covariance of xy. Right? Here x and y are two random variables. And in our particular case, what are the random variables? Both the estimates are random variables, beta 1 cap and beta 2 cap, right? They are random variables. They have different probability distributions, right? We have also seen the probability distribution of beta 2 cap earlier. So both beta 1 cap and beta 2 cap, they are following normal distributions. They have separate probability distributions. They are random variables, right? So we'll exactly use this formula. Here we have only minus. Instead of plus, we have minus. So the formula will be this. Variance of beta 2 cap plus 7 square. You will square this thing. 7 square variance of beta 1 cap minus. So if you square this, this minus will also be plus. So that is why. So plus of minus 7 square, that will be plus 7 square. So minus 2ab, 2a and then b is this. 2ab and then covariance of beta 1 cap, beta 2 cap. Right? So this will be the formula. Now, what is variance of beta 2 cap? Variance of beta 2 cap we found out earlier. Let me go back and check what was variance of beta 2 cap. See this. Variance of beta 2 cap is this. So simply substitute. So it will be 0.003206. This is variance of beta 2 cap. Now you have to find out what will be variance of beta 1 cap. So let me do that. Variance of beta 1 cap by the similar kind of formula. This will be x2y squared and the denominator will be the same. x1i squared summation I from 1 to n x2y squared summation I from 1 to n x1i x2y and a whole square of that. So sigma, this value we calculated beforehand. This is 0.009618. Then you have 3. In the denominator, you have 30 into 3 minus 0. So this value will come out to be, let me write it here only. It is 0.000326 0, and this is basically 0. 3 zeros and then this. So what will be the standard error? No, so you have to find out the variance only. Let's see how. You have to find out the variance only. So this is the variance of beta 1 cap. So you know what is variance of beta 1 cap, you know what is variance of beta 2 cap. Now only thing is covariance of beta 1 cap and beta 2 cap. So what will be that? Covariance of beta 1 cap, beta 2 cap. The formula is this minus. In the starting, you have a minus sigma u cap square summation I from 1 to n x1i x2i upon summation x1i square summation x2i square summation I from 1 to n x1i x2i whole square. Now this entire thing is zero. This value in the question, this is given to you as zero. That is why this entire expression will become zero. You don't need to take into account any other values. The numerator is zero means the ratio is zero. Right? So now you have all the formulas to calculate what will be variance of this. Now if you substitute the values of variance of beta 2 cap, variance of beta 1 cap and covariance which is zero. So this entire term is zero. The variance of, let me write the value, variance of beta 2 cap minus 7 beta 1 cap. If you put all the values, I have already done the calculation. This will come out to be 0.0189, something like this. It is a large term. There are many other values, but first terms are this, approximately 0.0189. This is the variance. So what is the standard error? Standard error is simply the square root of this term. So this will be 0.1375. Right? Now, if you have this, you can simply find out what will be the statistic. Statistic will be T computed. T computed. Now, in the numerator, what you will have this value, because this term is zero and this we have already calculated minus 0.33. So minus 0.33, and in the denominator you will have this 0.1375. So if you do that, you will find this to be minus 23,993. So what is the absolute value of T computed? Absolute value is 2.3993. And what is the T critical value? So critical value, we have got this earlier. This is two-tailed test basically. So 0.025, and then this value will be 97, right? N minus 3. N minus 3, n is 100, so n minus 3 is 97. This we have previously got to be 2. In the previous hypothesis testing problems also, in the first problem itself. Let me go back and see. So what was the critical value here? Yeah, see, this we have said this is approximately equals to 2. So now which one is greater? Which one is greater? Which one is lesser? So see, computed value is strictly greater than the critical value again. This is 0. Sure. Here you have one rejection region. Here you have another rejection region. And the value, computed value is somewhere here, 2.39. So clearly the T computed value exceeds the T critical value. So again, you are in the rejection region. So what you will write? We will reject H naught at 5% level of significance, and we will conclude. What you will conclude? You will conclude this thing, that beta 2 cannot be equals to 7 into beta 1, right? So conclude that beta 2 cannot be equals to 7 beta 1 depending on our given sample, at 5% level of significance, right? So this is how you answer all the 5 parts of this question. So let me do a quick recap of what we have done today. So we have taken it all in one question. This is a kind of question which gives you a holistic idea of what is MLRM all about. So that is why I have given you this question, because it touches upon all the aspects of MLRM, not only the estimation, but also the goodness of it, and also all kinds of hypothesis testing problems I have solved with you individual testing, individual parameter testing. We have solved joint significance testing, and we have also seen if there are interrelationships. Since there are more than two parameters here, more, many slope parameters. So you can basically extend many variables also. Here, x1 and x2 are the only two explanatory variables. You can add variables in your model, multiple linear regression model, but the formulas will remain the same. It's almost the same. Now, what you will do, if the parameters are given in this kind of a format where they have an interrelationship, then also you can test your hypothesis using the method that I have shown you. So for that, the estimation portion is this. This is the first part of the question. See, this is the estimation. You can basically take a screenshot if you want the formula. You can take a screenshot how to find out beta 1 cap OLS. You can take a screenshot how to find beta 2 cap OLS. Then how to find out R square. R square is simply ESS upon TSS. The formula of ESS and TSS are given to you. Again, take a screenshot or write it if you want to. Then this is the formula for adjusted R square, and I have solved the question. Now this is the individual test, two tail test. Now they can give you the variation like one tail test, only the right tail or only the left tail test. They can give you that easily. So in that case, only the critical value will change. The test statistic value will not change. Only the critical value that you have to find out from the statistics or econometrics books, that will change. From the T table, you have to find out the critical values. Only that much will change. The rest of the portions, as I've solved with you, that will exactly be the same. Right now, this is the joint significance test. If you want to jointly test the significance of the explanatory variables, you will follow this method. And finally, I have given you this question where you can find out the interrelationship. If beta 1 and beta 2 are related or not in certain way, you can test that also. And this is the output, right? So I hope you like this video, you find this video helpful. If you have any doubts anywhere, you can let me know. And if you find this video helpful, let me know in the comment section. And what do you think about this playlist? We have reached the end of this playlist. And if I get some new problems, some interesting problems, I will again update this playlist later on. Now, from the next day on, we'll be starting off with the advanced econometrics, where I will start off with the matrix notation. So in multiple linear regression model, we have only done the normal way. In the usual way, we have formed normal equations and solved them to find out the estimates and the variances. But now we will convert everything into matrix notation, and we will again again do all the things that we have done in econometrics. We will see what will be the CLRM assumptions now, how will be the violations of the assumption take place if heteroscedasticity, autocorrelation, multicollinearity, they are present in your model. How will they change if we use the matrix notation, and we'll see how to deal with that. And along with that, I will solve numerical questions, right? So that is the agenda for the next videos. As of now, if you like this video, give me a thumbs up and do subscribe to this channel, AN Economist, because that gives me immense motivation to continue making such useful videos for you. And stay tuned for the next video, and thank you so much for your time.